Okay, alternately we can solve this using the graphical method. I'm just making graphs. For the graphical method, we're going to get three choices. One is the concentration of A versus time plot is linear. That's going to be 0 order. Or two, the ln of A plot. We just look for which plot is linear or most linear. ln of A versus T plot is linear. This is going to be first order. Or the third option is if the 1 over A concentration versus T plot is linear. Oops. This one's going to have a different slope though. This one should have a positive slope. Then this is second order. All right, so this gives us our M here, our M value. The K value is going to come from the slope. And so here, if we want the K value, it's just going to be equal to the negative of the slope. The K value is positive, so we have to, if we have a negative slope, we've got to change it to a positive slope. The same thing here, K is going to equal the negative of the slope. But over here, the slope is already positive, so we don't have to change the sign. So we just say K is equal to the slope here. And so then we can figure out the rate law. The rate law is equal to K, A to the M. You know, this is only for the reaction. You know, AA goes to product. Here. So we don't have any other reactants. So, and then, you know, depending on M, we have the integrated rate laws. So we have 3 integrated rate laws that we look at. You don't have to memorize the integrated rate laws. Those would be given. You just have to know which one to use. That's it. All right, so let's take a look at the data and then see which plot comes out most linear. So go back to the original data. And here we're going to use all the data. We aren't just going to use the first 2. Go back to the data table. And then we'll just plot this in Excel. So here I'll put the concentration of A, and then over here I'll put the T in units of minutes here. And actually, let's see, which one is X? X is going to be, Excel, you know Excel, the order it does it? If I write it like this, then it's going to take A as my X and T. I'm going to swap these here. So let me cut this out, and then I'll just insert it over here. Oops. Let me insert it over here. Let me try that again. Okay, there it goes. Now it's going to be X and Y. And so I'm going to do 0 here, 1, 2. And then for A, I'll just plug in the concentrations, 1.512, and then 1.49, and then 1.469. Oops. Let's change that. There. All right. That's run 1, and then run 2. I'll just copy this. It was 3.024. starting. 2.935. And come on. $2.852. All right. So I'll select this data first and then just make a plot. And so insert. The chart I'm going to do is just an XY scatter chart like this. It looks pretty linear, doesn't it? But you have to recognize that we're only doing a really small percent reaction. I mean, this is like less than this 2.5% here. I'm looking at probably 5% reaction. So if we just look at a very small section of the overall curve, it's always going to look linear, because it's just a small. If we broaden this out, then we can see it's going to start slowing down, but it looks really linear to me. Well, you know, this is A versus T, and so we'll just do, this is going to be concentration of A versus T plot. And to see how linear this is we're going to insert a trend line. So I select a piece of data, right-click on that, and then add trend line. And then I want to do a linear trend line. When I do a linear trend line, I want to display the equation on the chart. So this is my equation there. Oops. And I want to, this is text options. Go back to this. And I want to display the R squared value. Wow, that's really pretty linear. That's really pretty linear because an R squared value of 1 means that the data points line up with that equation perfectly. And so an R squared is equal to 1 is just perfectly linear. All the data points are right on. Well, we got 3 9s and an 8. That's really quite linear. If it's 3 9s and an 8, and if we stop here and we say that this is the most linear, then it should be what order? It should be 0 order, right? But let's try the other and see what we get. So I'm going to move this data. The easiest way to make the others is just use Excel to do the calculation for us. So I'm going to do the ln of A. Okay, when I do ln of A, then I'll just equals natural log of this cell here, B3, and then enter that. And then I'll just copy and paste that down here. So the next plot I'm going to make is the ln of A versus T plot. In order to do that, I'm going to select my X data first, and then Control-click to select my Y data. I'm going to skip over the A. And then I'm going to insert a XY scatter chart. Wow, this looks linear too, doesn't it? That looks linear. And so ln of A versus T. And so I'll right-click on data, add a trend line. I'm going to go with a linear trend line, display the equation, and then display the R squared. Both of them look very linear. I'm going to go more sig figs here in this because this is 4 9s, but I don't know, maybe it's 5 9s. So what I'm going to do is I'm going to increase the number of sig figs here. So with this text box highlighted, I'm going to format it here. These are formatting options. So what are my formatting options here? Oh, here we go. Number. So the number I'm going to go as, instead of general, I'm going to go number here, and then I'm going to use more decimal places. Of course, if I just use 2 decimal places, it's perfectly linear, but that's round off error. I don't want round off error. So I'm going to go overboard here. I'm going to go like 7 decimal places. So as to see how many 9s I have. And so if I go 7 decimal, I have 4 9s and a 1. I'll go 7 decimal places on the previous plot and see what I have here. And so I'm going to click the text box. Oops. Let's move this plot out of the way. And just reformat the number. So I'm not going to go general number because then it just sets it for me. I'm going to go to number and then just set it to what I want. You know, and you have to be careful because a lot of people, they don't care about round off error, and they see that the A versus T and this versus T are both exactly 1, but it's not exactly 1. It's 1 to 3 sig figs. And so far it looks like the natural log plot is more linear because I have 4 9s. Here I only have 3 9s. But this is very dangerous. You know what's dangerous about this? What's dangerous about this is what I worry about this data is I don't have enough data. They only collected 3 data points for this curve, right? That means you're very susceptible to random error. And that random error could mean that just one slight random error here or there means the order changed, you know? And so this is quite risky. But then we have 2 experiments, so we'll see. You know, that helps lessen that. But, you know, something like this is practically the same. 3 9s, 4 9s. You know, it's hard to really gauge when you're thinking about random fluctuations, you know, unless it's super precise. If it's super precise, then we're good. All right. Then what we're going to do is I'm going to make one more column in my table. And the one more column is going to be 1 over the concentration of A here. And so I'm just going to set that equal to 1 divided by the concentration of A, which is cell B33 here. Enter, and then just copy and paste that down. Okay, and then I'm going to plot these set of data here by control. I'll click and drag here. And then I'll insert chart XY scatter. Okay, this also looks very linear. In fact, all 3 look very linear because we're taking such a small, short data set. We need to spread out the data. If you're going to collect 3 points, spread it out, you know. That way you can see the slowdown, if there is a slowdown. All right, so right-click, add trend line, and then display equation in R squared. When I look at the R squared, let's see, I'm beginning to think that's right on, exactly 1 to 99 or 100 sig figs. Excel carries 100 digits. But just to be sure, I'm going to carry this out to 7 digits. So over here, we're going to number. Instead of general, we use number. I'm going to go 7 digits out. So it wasn't exactly 1. You know, it was kind of deceptive. This is, what is this? 4 9s and a 7. So far, this one is the most linear out of the 3. But again, you know, we're talking, it's kind of risky. In thinking we're always that precise. So what I'll do is I'm going to copy these equations here by just selecting that. I'll copy it here and paste it here and then just drag it. And so we're going to make the same 3 plots here for trial 2. And see what trial 2 gives us. Because what you might find out is trial 2 conflicts with your trial 1. If trial 2 conflicts with your trial 1, what do? You know, this is what happens in research quite a lot. If everything worked out perfectly, then you'd get out of there so fast, you But people end up taking a lot of time because the results are conflicting. Like, for example, when you're doing your assignment for your unknown acid, the molar mass might match better with acid A, but the pKa matches better with the acid B. Which acid should you go with? Well, then you look at the percent errors, and maybe you have a larger percent error, even though the molar mass matches best, and then you have a very, very small percent error on pKa. Which one would you do? Those types of things make data analysis difficult. And that's why in scientific papers, the analysis part is separate from the raw data. The raw data is experimental facts, and this is what we call the results. But the analysis is your interpretation of the experimental facts. And so in the scientific literature, you'll see this happen sometimes. Somebody will read their paper and go, I don't agree with that. I come up with a totally different conclusion. And so they publish a paper taking this person's data and then just reanalyzing it there. This happens with like old data, and maybe the theoretical knowledge wasn't as clear back then, and so you'll see the paper's titled Reinterpretation of So-and-so's Data, basically. And so the data doesn't change because that's, factual, and so that's what we call results. But the analysis did change. That's what we call discussion. And so discussion and results are separate because we want to keep the facts separate from your analysis of the facts. Well, hopefully this agrees, because if this agrees, then that makes our life easier. At least we have two pieces of evidence that it points to second order, But we'll see. And, this is going to agree because I think this is all made up data anyway. But in real data, you have random errors, fluctuations, and all of a sudden things aren't so easy. And that's why, like, in classes like this is kind of deceptive because you're always looking for the right answer, and sometimes the problems are made up to give you the right answer easily, without too much headache. In fact, zero headache. And then, but again, this looks very linear, and so this is going to be just the A versus T plot, run 2. Or label this better. Okay, let's see what we get. 3 9s and a 6. Since I'm doing the large number of sig figs, I'm going to change this to 7 decimal places. 3 9s and a 5. Okay, this looks very linear too. This is the ln of A plot versus T for run 2. Okay, 4 9s, already better. Let's see what it goes out to. 3 9s actually, not 4 9s. 3 9s and an 8 versus 3 9s and a 5. So far this is better, barely. Some people will say there's no difference, and you'll get people who argue with you that's saying that you're being ridiculous, in your analysis. But this is the best we can do, right? We should have collected more data. That way it would be much, much clearer. And that's a valid criticism because we're making something that could just be generated by noise. So when we write the paper, we're trying to answer all the critics. There are going to be lots of critics. When you write a paper and you submit it to a journal, they send it to 3 referees. Sometimes less. It depends on how many. And the referees are these volunteers who will go through and read your paper and then their job is to tear apart your paper. That's their job, and that makes the paper a lot stronger. And so, that's why they say peer-reviewed. But sometimes peer-reviewed journals they don't really review it much. I've read peer-reviewed journals, publications where I wonder how it got past peer review process, because some of the experiments they did was clearly made up data. It seemed like made up, somebody just wanted to graduate and it wasn't caught. There was a case where the very famous scientist made up data to get published, and it was found out, and then they ended up committing suicide. It happened. It's a true story. But there's so much pressure. Well, anyway, this agrees. 4 9s and an 8. 3 9s and a 5, 3 9s and an 8 and a 4 9s. So this agrees. And so we're going to say second order. That's the best data we have, And of course, this is the great thing about a paper, because what you can do is you can answer the critics right away, Even though we would have liked to have more data, and even though this could have fallen within the noise region, this is the best interpretation of the data we have at this point. And then the critics will have been satisfied, But you put that in the paper in the discussion section, and it's better than saying, oh, this is absolutely second order. There's that risk that, because of the noise, it might not have been. And so this is the big benefit of writing a scientific report versus just filling in the blanks on some report sheet, Okay, so now all we have to do is this. This is our K value. It's going to be 0.00997. And it's actually, we have 2 K values. And both K values should be the same. So from run 2, we get a K value or slope of 0.00997. So let's go ahead and put that in here. 0.0099717. I'll just do it like this. And then from run, this is run 2, so let me put that down here. And then from run 1, our K value was 0.0096798. 96,798. 0.0096978. Both K values should be the same. It's the exact same reaction, just different concentrations. So what we're going to do is we're going to take K average. When we take K average, this is going to equal this plus this, and I need to divide the whole thing by 2, so I'll put the parentheses here, divided by 2. And so the K average comes out to 0.009835, and therefore the rate law is rate is equal to the K average, 0.009835. Actually, how many sig figs are we allowed? We're only allowed, I think, 2, said? So 0.098. Now, what are the units for the K? The units are going to be inverse molar, inverse time. And so this should be molar to the -1, and then T or minutes to the minus 1. Okay. And then A squared. I don't know if I can do superscripts here, but I'll just do this, the hat 2. That would be a rate law. So how does this rate law compare to the rate law we had earlier from the previous analysis? So from earlier, we should get the same rate law, but this one's relying on a little bit more data than the previous one did. And so this one may be more reliable for the K value, I would think. We got 0.097 for the K value in second order, 0.097. For this analysis, that didn't work. .098, pretty close. Okay, so that's the graphical method. What's another method for solving? So we use method of initial rates, the graphical method. The next method we use is, are you going to have access to Excel during a test? No. And so the next method that we're going to use is what's going to be called K analysis. I call it K analysis or slope analysis. And so let me talk about what I mean by K analysis or slope analysis. This one is only 3 points. So let's consider the graph. There are 3 points here. If these 3 points were truly linear, then the slope of segment 1 should equal the slope of segment 2 here. So what we do is we figure out the K for this segment, which we'll call K segment A, and then we'll figure out the K for segment B. And then what we're going to do is we're going to calculate the percent difference. They should be exactly the same if it's linear, right? If it's linear, the slope shouldn't change. So I'm going to solve the integrated rate laws for K. And so we'll start off with zero order. K for zero order is going to equal A at time t minus A at time 0 divided by t. Okay, then we go with K for segment A. So we'll try this here. K for segment A is the initial was 1.512. What was the final? go back up here and look. So the initial is 1.512, the final is 1.490. And that segment has a time interval of 1 minute. And so .022. Yeah. Oops. Oh, this should be a negative here. Negative KT. So this is going to be plus 0.022 molar per minute. All right, that's the first segment there. The second segment, what we'll call just KB here, is going to have these 2 points. So what we're going to do is our new initial is going to be 1.49. We're looking at the slope between these two. So 1.49 will be our new initial, and the final will be 1.469. And the time interval here will be 2 minus 1 is 1 minute time interval for segment 2. So 1.469. So our final will be 1.469. Our initial will be 1.490. The end of this one. And our time interval will be 2 minus 1, which is just going to give us 1. This will be molar per minute. And so 1.469 minus 1.49, 0.021. Now these look very close, but what we need to do is we need to calculate the percent difference between these because it's all kind of relative. And so the percent difference is we take the biggest minus the smallest, divided by the smallest, times 100%. And so I'll take the biggest minus smallest and divide it by the smallest. And I get a 4.76 times percent difference. And so the slope changed by 5%. Would you say that's significant change in the slope? Yeah, I would. All right, so that's 0 order. And then we're going to go to first order and see if we get a less significant change in the slope. You know, the first order, we're looking at the ln plot. And the ln plot is linear. And so K, I'm just rearranging it, is going to be equal to ln of A at time t over A initial, or A0, divided by t. This is going to be negative. The time interval. So let's go on to Ka. Ka, we had, this is going to be minus ln of A at time t. A at time t was 1.49. And A at time 0 is 1.512 divided by t, which is 1.0 minutes. So I'm going to go ahead, 1.49 divided by 1.512. equals, take the natural log of that, divided by 1. So this comes out to 0.01465. I'll just go extra digits just to make sure. 0.01465. And the units here are going to be minutes to the minus 1. All right, for the second segment, we have KB is going to equal minus ln of the final. The final for that segment is, just get it here, 1469. And the initial for this segment is 1490. Divided by the time interval is just going to be a time interval of 1 minute again. So I have 1.469 divided by 1.49 and take the natural log of that. And I get 0.01419. Okay, now this is minutes to the minus 1. It's hard to gauge I mean, 1465 versus 1419 seems pretty close, but let's take a look at the percent difference. So I'll take the biggest, which will be 1465. 1465 minus the smallest, which will be 1419, divided by 1419. 3.24%. So the previous one, the slope changed by about 5%. This one is changing about 3%. So this is better. This is more linear. Right. Okay. All right. Now we're going to try second order. This is just for run 1. Now for second order, the K is going to equal 1 over A at time t minus 1 over A at time 0 divided by the time t. And so for segment 1, it's going to be 1 over 1.490 minus 1 over 1.512 divided by 1.0. The units here are going to be molar to the minus 1, minutes to the minus 1. And so we do 1.49, and I just hit the invert key. 1.49 invert minus 1.512 invert. Invert equals, and I get 0.4. This is Ka. Sorry, 0.4438. Just go 4 digits. Molar to the minus 1, minutes to the minus 1. Oh, you did? Okay, what did you get?
9.76 times 10.
Yeah, I was going to say there's a mistake here because this K is way off. We expect 0.0097, 0.009 something. So I made a mistake here. So, Mina, can you tell me again what you got? 0.009765. Thanks. All right, let's do KB, which will be 1 over 1.469 minus 1 over 1.490. Just our ending and our starting point over this 1 minute interval. And what do we get here? I'll try it again. Oh, I see what I did wrong. My calculator hit the wrong key. So I'll just do 1.469 invert minus 1.49 invert. I get point. Why does it keep doing that? I hit the minus key and it keeps multiplying it for me. Do you have it, Mina?
9.594 times
9594. Okay. So here, I mean, the 9765 versus 9594. I don't know. I have no idea. So the thing we're going to do is calculate the percent difference here. So 9765. $97.65 minus $95.94. Divided by 95.94. 95.94 is smaller. 1.78. And so the one that has the smallest percent difference should be the most linear. So this is the most linear. Between the slopes of the segments. And the best slope is just going to be the average of these two because, you know, of the random fluctuations, we collect as much data as possible and average it. And so we're going to go 0.09765 plus 0.009594. Divided by 2. And we get 0.0967. Molar to the minus 1, minutes to the minus 1. A squared, second order. We'll round this to the correct number of sig figs, 0.097. Molar to the minus 1, minutes to the minus 1. A squared. So essentially the same. This is from run 1, and then we'd repeat it for run 2. You know, because the more data we have, the more convincing our analysis will be. And so here, run 1, repeat calcs for run 2, which I'm not going to do because it's going to take too much time, and average. The K values. The M value is not going to change. I mean, I think run 2 will also give us second order. You know, this is most linear, which was second order. Okay. All right, so this is the third method that we could use K analysis. And K analysis is good if you don't have that much data. You don't have to calculate that many slopes. If we have 3 points, we have 2 segments. If we have 4 points, we'll have 3 segments. If we have 5 points, well, you know. And so it depends on how many points we have. If we have a lot of points, then you don't want to be doing K analysis because it's going to be just too much work. The last method we have is the hybrid method. This hybrid method will be discussed in it will be discussed later for the kinetics lab. We're going to do the kinetics lab using a hybrid method, graphical and method of initial rates. And one other method, the hybrid method is going to use a trick. And so I should say, let me say one thing here. The hybrid method uses a trick. What is that trick? Well, if we go to the kinetics lab, the rate is going to equal K times the crystal violet concentration to the M and the hydroxide concentration to the N. We have two reactants here. The two reactants are crystal violet ion plus hydroxide ion, and then made crystal violet hydroxide. The problem is when we use the graphical method doesn't work here. Because the graphical method is going to give us the overall order of reaction, but it's not going to give us M and N. So the graphs are going to be based on M plus N. So if M plus N is equal to 0, then we'll have a 0 order graph. But if M plus N is equal to 0, how are we going to figure out what M is, and how are we going to figure out what N is? Because there are an infinite number of possibilities that lead to 0. So for example, it could be 0 plus 0, it could be 1 plus negative 1, it could be 2 plus negative 2. You know, not all infinite ones are feasible. Like, we wouldn't expect a million plus negative million, right? Or would we? We need to know the theory to understand. Is that even feasible, a million plus negative a million? Right. So what we do is we do a trick. And this is the trick we do. The trick is we make this hydroxide concentration so high, so large, that it remains fairly constant over the course of reaction. So if the hydroxide concentration doesn't change, then it's not going to impact the rate. I mean, right? And so as the reaction progresses and the hydroxide stays the same, then nothing happens with the rate. But the hydroxide concentration has to be so large that you barely eat into it over the course of the reaction, so it barely changes. And so if we can make it, if we can make the hydroxide concentration constant, that is the initial and the final, you know, are about the same, you know, then the hydroxide is constant. If that's the case, then what we do is we do this. We say the rate is equal to K, and then I'm going to put the hydroxide here. And this is going to be hydroxide. It's still to the N power. And this will be the crystal violet over here to the M power. And then we're going to roll this into a new constant. And that new constant is called K prime. And this will be times the crystal violet concentration to the M. So now we only have this dependent on the crystal violet concentration. So as the crystal violet concentration changes, so does the rate. And so this is called pseudo-M order. It's a trick. We can do the same thing. We can keep the crystal violet very high. If we keep the crystal violet very high, then the rate only depends on the hydroxide concentration. We could do that as well. So now the graphical will work, because the graphs are only going to be based on M, not M and N. And so we'll just make plots of the crystal violet concentration versus time, and then we can see which one's most linear, and then we can get M. But then that leaves the question, how do we get N? The way we get N is we do 2 runs, and we'll just double the hydroxide. And if we double the hydroxide is already so large, it barely changed. If we double it, it's going to change even less, right? And then we see, if we double the hydroxide, what happens to the rate? Did the rate double? Or did it stay the same? Or did it quadruple? So pseudo M order, or pseudo, we could make it pseudo M order, pseudo N order, pseudo O order. We just keep everything very large other than what we're interested in. And so M, it could be whatever. It doesn't have to be M. But this is a common trick that's done. But, what we want to do is, why can't we figure out what M and N and O are without having to do experiments? And so our theoretical analysis is we want to dig deeper. Okay, now we have all these equations we can figure out, make predictions, which is fine. This is like the ideal gas law. You can just use these equations to make predictions about pressure, volume, temperature, moles. But what we want to do is we want to figure out what is the origin of M, N, etc. Where do these numbers come from? They don't come from the balanced chemical equation, or do they? Sometimes they match, sometimes they don't. And so we want to figure out the origin of M, N, and then we want to understand K better. What is this rate constant? The bigger the rate constant, the faster the reaction, right? The smaller the rate constant, the slower the reaction. But what does the rate constant depend on? And so these are questions that we need to address at a deeper level. So once we have the laws already, the equations, then we start to think about some kind of hypothesis and some kind of theory. Well, somebody's already done that. And so we're going to get into the theoretical analysis and then try to figure out where M and N come from. The origin of M and N come from something called the mechanism of the reaction. And K we look at in terms of collision theory. Actually, both of these are under the theory. The theory here is going to be collision theory for chemical reactions. So the hypothesis goes like this. When we have a chemical reaction, the things have to collide. So for example, if you have a solid plus solid, it's kind of slow. Solid plus solid reaction is very slow. However, if you heat it up, it could go much faster. Things with very large driving force don't necessarily go fast. Depends. We'll take a look at something that goes kind of slow. Let's see if I have it still. I want to find the, it doesn't come up quite yet. I can't remember what they're called. It's these guys here, thermite versus car. Let's see if I can get the video up. With the audio. I want to get the original video. So I need to get the name. Have you seen this? All right, let me show this. They don't have the name. Thermite is a mixture of rust and aluminum metal. Would you expect rust, which is a solid, and aluminum metal to react very fast? No, they're both solids. The only way you can get them to collide is to hammer them or to figure out some way to get them or heat it up. And so we could heat it up. These guys had a lot of videos up, but thermite versus car. Diesel power. The Brainiacs, that's what it was. Brainiac.gtgs. Let's see if the audio's. Audio's not working. Plus the resolution on this video is bad. I'll show it again later, but it's just a show. This actually has a pretty large negative delta G. It just goes like that. However, if we have gases can potentially react much faster, but the problem with gases is that gases consist mostly of what? Gases consist mostly of empty space. And so liquids can potentially react extremely fast as well. There's a lot more collisions there. But gases have more kinetic energy. And so these are all things we balance out. And so let's take a look at collision theory. When we have a collision, let's pick two molecules, an A2 plus B2 molecule. And this is going to yield two ABs. Now, we're going to make the ABs more thermodynamically stable. And so normally what we do here is we have this. We'll have A2 plus B2 up here in terms of, let's go with enthalpy here. And then two ABs down here. Now delta H is just a state function. And so delta H just depends on the final state, which is down here, H final, minus the initial state, H initial up here. But what kinetics is kinetics is path dependent. Kinetics depends on how you do the reaction. And so what we're going to do is for kinetics, we're going to see what's in between. How did it get from the initial state to the final state? And so what we do is we have a reaction. This is called a reaction coordinate diagram. The reaction coordinate diagram follows the progress of reaction here. And so normally our energy level diagram just consists of this, but in kinetics our energy level diagram is going to consist of this, because what we're going to try to do is we're going to try to figure out how it gets from here down to there. This is the origin of M and N. M and N and O come from this. M, N, and O. We don't see it over here, because all we care about in the state function is the final state and the initial state. And so what happens in collision theory is this. We take the A's, let's go with like this, A here, and B here. We take these two molecules and then collide them together. And they have to collide with enough energy to break the bonds. So what we're going to do is we're going to have to climb up this hill here. And we'll have to break the bonds here. And so what we end up with is a state where the AA bonds are breaking and a state where the BB bonds are breaking. But at the same time these bonds are breaking, the AB bonds are forming. And so this species here is called a transition state. We don't actually isolate this, but this would be a transition state. It's a transitory state in going from the reactants to the products. There could be multiple transitory states. This is just one of them. And so this is a transition state. A transition state is a state in which the bonds are being broken and formed at the same time. And it's going to correspond to the peak energy. The peak energy here doesn't mean that it's just the bond energies. It's a little bit less than the bond energies because bond breakage is endothermic, bond formation is exothermic. So this is a little less than the bond energies of A and B here. And then it could happen in multiple collisions. If we have multiple collisions, then this is more complex. And this is called the mechanism. In this particular mechanism, it's just one step. Boom. We form this transition state. Now, the transition state has two options. The transition state can fall back down to the left or it can fall back down to the right. If it falls back down to the left, then we reform the AA bond and the BB bond. If it falls back down to the right, then we're going to form the AB bonds. And so what we'll do here is we're going to continue the progress of the reaction. The progress of the reaction is going to just fall down here. And then what we're going to form is we're going to form the AB bond here and another AB bond here, and we'll get two ABs. Now, as far as energetics go, now we have more terms that we have to deal with in addition to delta H. Our delta H is still the same. Our delta H has not changed. And so the delta H is still this drop here from the initial to the final. That's our delta H. However, we have another energy term here. This other energy term is going to be here. We have to climb this little hill first. And climbing that little hill, we assign that EA forward. Or we have to climb the big hill to go backwards. So let's say we are at the product and we want to go back to the reactants, reverse this reaction, then this is going to be EA for the reverse. So when I look at the forward, it has to climb this little hill, but if I try to go backwards, it's got to climb this gigantic hill here. It's EA reverse. Most of it's going to stay down here. What is EA? EA is the activation energy. We call it the activation energy. So, in collision theory, there are two requirements that we have to have for a reaction. These two requirements that we have to satisfy for a reaction is one, we have to have the correct orientation. That is, the A's and the B's have to be lined up. So if they're misaligned, then we're not going to get reaction occur. And when we think about it, it's just random, the random position, and therefore, the actual percentage of molecules that have the correct orientation is minimal, extremely small. And so they do some numbers, like if you had, let's say, 1 billion collisions, how many of those have the correct orientation? A very small fraction of those. And therefore, You know, if you have 1 billion collisions and each collision was successful, then we'd have an explosion every time we had a reaction because it happened so fast. Okay, we need the correct orientation, and the second thing we need is we need the correct energy. You know, it has to have greater than the EA, and so we need EA minimum. A lot of collisions don't. And so when we think about energy like this, then we always think in terms of what distribution. What is a thermal distribution or energy distribution that comes to mind? Yeah, good. We always think, when we think in terms of energy, we always think of the Maxwell-Boltzmann distribution or the temperature distribution or the thermal distribution or whatever you want to call it. Do you know the equation for the Maxwell-Boltzmann distribution? The Maxwell-Boltzmann distribution is what we call an exponential function. Do all molecules have enough energy? No. Usually there's going to be a cutoff. And so when we think about this, we sort of visualize the Maxwell-Boltzmann distribution. And then what we're going to do is we're going to put a minimum energy here. The minimum energy cutoff is going to be called EA here. And so this is our EA. And then any molecule above this has enough energy, but maybe not enough, maybe not the correct orientation. Okay. And so, you know, the more molecules that have this, the faster the reaction will go, and the more they have the correct orientation, the faster it will go. And so this brings us to the theory of the rate constant. The theoretical interpretation of the rate constant is the rate constant is going to depend on A, which is called a pre-exponential. This is the collision factor. This factors in, you know, what percentage of those particles have the right orientation. And so we call this the collision frequency. And then we get the Maxwell-Boltzmann. The Maxwell-Boltzmann is an exponential function, and then we have the EA cutoff. So we'll put in the Maxwell-Boltzmann and have this minus EA over RT in here. And so the rate constant depends on the collision frequency and the thermal distribution, thermal population distribution. Does that make sense? So, of course, if we increase the temperature, what happens to the thermal population distribution? If we increase the temperature, then we're going to get a higher population, right, of higher energy. And so increasing the temperature makes T bigger here, which makes this term bigger, which makes K bigger. The other thing is we could decrease the activation energy to speed it up. If we decrease or increase the activation energy, let's say we decrease the activation energy, it makes this term smaller, which makes K smaller or bigger. Actually, no. If we decrease the activation energy, that makes this term bigger and K bigger. If we increase the activation energy, then the K should go small. Does that make sense? Just based on the math. And so this is the theoretical interpretation of the rate constant K. Okay. Now, the other thing we need to figure out is what is the interpretation of this, M and N. M and N are easy here because this is a simple mechanism. For simple one-step mechanisms, then we have this. Let's say I have AA plus BB yields product. If we have one step, then the rate for this step is equal to K of this step, A to the little a, B to the little b. So in other words, A is here and B is over here. So let's just take a look at this particular reaction here. We have A colliding with B, or B2. This is A2 colliding with B2. If I double the number of A2s, do you know what happens? I double the number of collisions. If I double the number of B2s, I'm going to double the number of collisions. If I double A2 and B2, I'm going to quadruple the number of collisions. Think of colliding with a wall. If I have one molecule colliding with the wall, I get one collision. If I'm going to double it now. Now I have two molecules colliding with the wall, I'm going to get twice as many collisions, two collisions, right? Three molecules colliding with the wall, I'm going to get three collisions. So, so it depends on the molecularity. And so here I have A2 plus B2. A2 plus B2 is going to yield two ABs. And so the rate for this step is equal to the A2 concentration to the first and the B2 concentration to the first, because the coefficients are 1 and 1. 1 A2. All right. Let's take a look at another one here. Let's say I have two A2s colliding. Actually, I'm not going to look at it quite this level. I'm just going to say A2. In other words, two A2s go to product. I'll just do it like this. And so the rate is going to equal K A2 squared. Now, where do I get Ka 2 squared? The way you can visualize this is I'm going to have an A2 on the left. And if I double the A2 on the left, I'm going to get twice as many collisions, correct? And then I'm going to have an A2 on the right. And if I double the number of A2s on the right, I'm going to get twice as many collisions. So if A2 is the same as A2, and so if I double the A2s, I'm doubling the A2s both on the left and the right, and I'm going to quadruple the number of collisions. And therefore, it's got the squared dependence here. Now, the reason why we use M and N is for multi-step mechanisms. If it were just one step, we wouldn't have to do this. The reason we use M and N is because of the possibility of multi-step collisions or multi-step mechanisms. So for example, we could have something like this. Let's say we have a reaction that starts off here, and so we're going to follow the reaction progress. As we follow the reaction progress, there's going to be a collision here, boom. It's going to form a transition state, and then it's going to drop down. But in this case, it doesn't drop down all the way to product. In this case, it drops down into what we call an intermediate product. Here. And then we have another collision, boom, here. And this one drops down into another intermediate product. Here. And then we might have another collision here, boom. And then finally we drop down to product. Here. And so this is going to go through three transition states. The three transition states will be a transition state 1, another transition state 2, and another transition state 3. And this is going to go through two intermediate products. And so this is going to be intermediate product 1, intermediate 1, and then intermediate 2. And then this is going to be the reactants, this is going to be the products here. So in thermal, all we care about is our delta H or delta G or whatever. I'll just say delta H here. But in kinetics, we care about the path. How did it get there? And this path is going to be a more complex path, because when we look at the initial collision, that's not the biggest mountain to climb. Which one's the biggest mountain to climb? That's going to be the second one. Do you see that? Because this one, let's say you're a group of bicyclists. You're a group of bicyclists, and everybody has to stay together. And so the fast person and the slow person, we got to wait. And so if you're a group of bicyclists, then okay, we make it over here. But you know, the biggest hill here is going to be what we call the rate determining step. This is going to dictate how fast the whole group moves through it. And so it's going to be the biggest challenge. And so here, well, it depends on what the collision is here. The collision here is different than the collision here, which is different than the collision here. So we have different collisions. And so we don't know what the collision is here. You know, it's not so simple. In fact, let me give you a more complex example here. And so this is still relatively simple. An example is the combustion of methane. How long has the combustion of methane been around? Combustion of methane's been around for ages. However, do you know it wasn't until recently, like the 1970s, I think, that somebody finally figured out all the possible steps in the mechanism? Well, it depends on what paper you read, but they're about anywhere between like 500 to 2,000 steps possible. There are a whole bunch of intermediate products. You know, you look inside the flame, what do you see? For example, what gives you a blue color? This burns with a blue flame. Does water give you a blue color? You tell me, what gives you the blue color? What's giving you the blue color is atomic oxygen. It's an intermediate product. You know, there's a whole bunch of stuff going on in that flame. But anyway, we're out of time, so we'll talk about this more later.